Hello everyone, and welcome. If you're a first-year engineering student in KS 23003, this explainer is specifically for you. We're going to break down everything you need from your course book to really nail Quiz 1. We'll be talking all about how to measure a signal's strength using its energy and power, and then how to classify it. So let's get right into it.
So here's the game plan. We'll start with the why. Why this stuff actually matters in the real world. Then we'll jump into the formulas. After that, we'll define the three main classes of signals, work through a few examples together, and I'll even give you a little challenge to test your skills. We'll wrap it all up with a simple checklist that you can take straight into your quiz.
All right, first things first. Why are we even bothering with all this? Well, these concepts of energy and power, they're not just some abstract math problems. They are absolutely fundamental to how we design things in the real world.
I mean, just think about your phone. Every single Wi-Fi or Bluetooth signal it sends out has a total energy. And where does that energy come from? Yep, straight from your battery. So a signal that requires a lot of energy is going to drain that battery much, much faster. This is exactly why understanding signal energy is so crucial if you want to design a device with a battery that actually lasts. And what about power? Well, a signal's average power is a huge deal for designing the hardware itself. If you've got a radio transmitter or an antenna that can't handle the average power of the signals it's supposed to send, it's going to overheat and fail. Simple as that. So to put it simply, energy is all about the total juice you need, while power is about how fast you're using that juice. Okay, let's move on and see how we actually measure these things. We've got two key formulas that are basically our main tools for the job. And don't worry, they look a little intimidating at first, but they're way more straightforward than you think. And here it is. This is the big one for total energy of a continuous time signal, x of t. It's just the integral of the squared magnitude of the signal, and we're looking at it over all of time, from negative infinity all the way to positive infinity.
So what is this formula really telling us to do? Well, first, you take the signal's magnitude and you square it. The reason we do this is super important. It makes sure that every part of the signal, whether it's positive or negative, gives a positive value to our total energy. Then you integrate. And, integration is really just a sophisticated way of summing up the signal's strength at every single moment across its entire existence.
Now for our second formula, the one for average power, you can see it looks pretty similar, right? But there are two key differences. First, we're integrating over a finite window, from negative t to positive t. And second, we're dividing by the length of that window, which is 2t. Then, for the final step, we see what happens as that window gets infinitely large.
This really just breaks down the idea of an average. Just like before, step 1 is to square the signal's magnitude. But instead of summing up everything for all of eternity, we just sum it up over a very, very large window. Then, we divide by how long that window is. What that gives you is the average energy per unit of time, which is exactly what power is.
Okay, so you've done the math, you've calculated your E and P values. Now what? What do these numbers actually mean? Well, this is where classification comes in. Your results will sort any signal into one of three very specific categories.
This table is basically your roadmap. So, first up, if you calculate the energy and get a finite positive number, you've got an energy signal. And it makes sense that its average power would be 0, right? Because you're spreading a finite amount of energy over infinite time. Now, what if the energy is infinite? Then you move on to calculate power. If the power is a finite positive number, it's a power signal. Think of something that goes on forever, like a perfect sine wave. And finally, if both the energy and the power turn out to be infinite, well then it's classified as neither.
Theory is great and all, but let's make this real. We're going to apply these formulas in that classification table to three different signals that you are pretty much guaranteed to see in your coursework.
First up, the decaying exponential, e to the minus t times the unit step. So we start by calculating its energy. We square it, which gives us e to the minus 2t, and then we integrate from 0 to infinity. That's because of the unit step function. When you work through the integral, the result is a nice clean 1/2. Since that energy is a finite number and it's greater than 0, we can stop right there. We know it's an energy signal.
Next, we've got a classic sinusoid. Now, for any periodic signal like this one, its total energy is going to be infinite just because it repeats forever and ever. So we don't even bother with the energy calculation. We jump straight to power. And here's a great shortcut. For any sinusoid that looks like a cosine omega t, the average power is just the amplitude squared divided by 2. In our case, a is 3, so the power is 3 squared over 2, which is 4.5. And since that's a finite, non-zero number, this is a power signal.
And for our third example, we've got the simple ramp signal.
x of t equals t. This signal just grows and grows without any limit as time goes on. So if you try to integrate its square, t squared, over all time, the energy is obviously infinite. And it turns out, if you go through the calculation for its average power, that also goes to infinity. Since both E and P are infinite, we classify this one as neither.
All right, so you've seen the process in action. Now it's your turn to give it a shot. This next part has a quick challenge for you, and we'll also talk about a very common mistake you'll want to avoid.
So here is your challenge problem. Your job is to classify the signal x of t equals 2 times e to the minus 2t times the unit step. This looks pretty similar to our first example, doesn't it? So you should know exactly what to do.
Seriously, go ahead and pause this explainer right now, get out a piece of paper, write down that energy formula, and see if you can work through the integral. Let's see what you come up with.
Okay, are you back? Let's check out the solution. First, we set up our energy integral. We square the signal, which gives us 4 times e to the minus 4t. The integral of that is negative 1/4 e to the minus 4t. We evaluate that from 0 to infinity, multiply by that constant 4 out front, and we get a final answer of exactly 1. Since the energy is finite and positive, this is an energy signal. So how'd you do? And that leads us to a really important warning, and this is taken straight from your course book. It can be super tempting to see a signal that's decaying towards 0 and just assume, oh, that's an energy signal. But that is not always true. Some signals actually decay too slowly, and their energy integral might not converge to a finite number. So the main takeaway here is you have to do the math. Always evaluate the integral to be certain. Okay, let's wrap this all up. We're going to put everything we've talked about into one simple, foolproof checklist that you can use to get ready for your quiz. And here it is, your 3-step process for any classification problem you're going to face. Step 1. Always calculate the total energy E first. If you get a finite positive number, you're done. It's an energy signal. Step 2. If the energy is infinite, then you go and calculate the average power P. If P is finite and positive, you can stop. It's a power signal. And finally, step 3, if you found that both E and P shoot off to infinity, then the only option left is neither. It really is that simple.
So we'll end with one last question for you to think about. You now have the tools to analyze a signal's strength. So how does knowing if a signal is an energy signal or a power signal actually change your approach to designing the electronics, the battery, the antenna, everything needed to handle it? That right there is the bridge from this fundamental theory to real-world engineering. All right, good luck with your quiz.